Good morning class and welcome to our continuing course on sustainable energy technology. In the previous class we ended with by comparing the different types of energy storage technologies in terms of their basic performance characteristics. We will continue this discussion a little bit more by looking at this in a graphical way. So these are two very important characteristics that we discussed. The energy density in terms of watt hours per liter and power density in terms of watts per liter. So again, liter is decimeter cube because often we think of liter as liquid, but it's basically a volume unit. So it is basically giving you how much power it can store in terms of power it can deliver per unit volume of the storage material and how much energy it can store per unit volume of the storage material. Those two are somewhat different because one can have a low energy storing device with high power absorption and delivering capacity, okay, and vice versa. A good example of such a device is a capacitor. Capacitor has a very high power density in terms of watts per liter. It is going to 100,000 or more. Note here in this graph, let me use the laser pointer. This is a logarithmic graph. So it turns from 1 watt per liter to 100,000 watts per liter in steps of 10. Similarly, the energy density is also a logarithmic curve, 1, 10, 100, 1000, 10,000. So this is say 100, this is 200, 300, 400, 500, 600, 700, 800, 900, 1000. So the values here are non-uniformly distributed. So that needs to be remembered because it's a log-log plot. So here capacitor has a very high power density and quite low energy densities. So power density is 100,000 watt per liter. Energy density can vary from 1 watt hour per liter to around 10 watt hour per liter. Okay. Supercapacitor is an improvement on the energy density side. So again, as we shift from a standard capacitor to a supercapacitor, its ability to store energy per unit volume increases, and here the supercapacitor will go from 10 watt hour per liter to around 30 or 40 watt hour per liter. Okay, whereas the power density remains the same as that of capacitors. Okay, so that is in the high power, low energy range. Is there anything on the low power, high energy range? Not that much. Maybe the best we can talk about is the zinc flow battery system, which has a reasonably large energy density of around 50 watt hour per liter, as we can see here, and low power densities of around 1 to 10 watt per liter. Okay, this is the lower high energy density, low power density range. There is a lot of systems which have both low power density and low energy density, pumped hydro storage, compressed air energy storage being the two best known examples. So given that this is not volumetrically efficient either in terms of power or energy, the reason we use that is its cost competitive, and you can actually store large volumes, and you are basically you are using air and water. You are not constrained by material cost, so you can get away with that. Okay, otherwise this will not be commercially realizable at all. Okay, and we are seeing low power, reasonably medium energy density are the various flow batteries here. So this is vanadium redox flow batteries, zinc flow batteries, etc. Potassium sulfur batteries, those kinds of battery systems. In the medium term here, you see systems with reasonably good power density, not as good as capacitors, but still quite good, 1000 to 5000 watt per liter range. At the low energy densities, you have the superconducting magnetic storage, which have energy densities less than 10 watt hour per liter. Flywheels have good power density and energy density is comparable to batteries, which makes it a very good energy storage choice for many applications. So here flywheels have power densities of 2000, 3000, 4000 watt per liter, and energy density is ranging from 20 to around 80 watt hour per liter. So very similar to many of the other batteries that we have, nickel, cadmium, lead acid batteries in terms of energy densities, but significantly higher power densities. Okay. Of course, there are other aspects. Flywheels usually lose energy much more quickly than batteries, so those things are not being discussed here. Okay. Sodium sulfur is here, reasonably good power density and high energy density. One of the higher energy densities in terms of batteries, which makes it a good choice for stationary energy density applications. And also because sodium and sulfur are reasonably cheap material for energy storage. Lithium ion, we can see why lithium ion is favored. Good power density and highest energy density among all battery types. It is going above the 100 watt hour range like sodium sulfur, but it is also delivering power densities above 1000, which no other batteries can deliver. Okay. So it is power density of 200, energy density of 200 to around 500 watt hours per liter, with power densities going from around 1000 to 8000, 9000 watts per liter, okay, making lithium ion a very good energy storage medium. Reasonably comparable to lithium ion and with even higher energy densities. In fact, the highest energy densities among all this is your fuel cells, which run on hydrogen. So here we are comparing a hydrogen based energy storage system with lithium ion, and you can see fuel cells have a highest energy density among all these systems. Here you have energy densities ranging from around 500 watt hour per liter to around 3000 watt hour per liter, and power densities lower than lithium ion but reasonably comparable to the other batteries of around 500 to 600 watt per liter. Okay. So fuel cells have a unique advantage of the highest energy densities and reasonably good power densities as well. Okay. So this is also the reason why hydrogen energy storage is being looked at so seriously in the recent years. And these are some of the energy storage technology uses. We have discussed this a few times before. This is the discharge time at rated power. Seconds, minutes and hours. And system power ratings in terms of module size. So largest size are pumped hydro and compressed air. So it is extremely high volume systems, 100 megawatts to 1 gigawatt. And so these are in bulk power management systems. For power quality discussions, we want we do not need that much power, but high good response times in seconds, minutes, hours. So this is where you are getting supercapacitors, flywheels, batteries, high energy supercapacitors, etc. In between, you have large module sizes, and you can go from seconds to hours. So this is usually used for transmission and distribution, grid support, load shifting, etc. And here also all the battery types are important. The flow batteries and the sodium sulfur battery are specifically applied for this section. Lead acid battery can be used for both. The superconducting magnets can also be used here. Flywheels can also be used here. Okay. So this is another way of distributing the technology applications between the various storage systems. So we will close this section of comparative systems by looking at the key energy storage technologies and their projected improvements in the future. Okay. So this is the current data 2016, and this is the projected technology development by 2030. Especially for less mature technologies, this is important because that will help us see where the R&D is and what is the expected progress in the next decade. Okay. So here, when you are looking at pumped hydro, which is a very mature technology, nothing much actually changes. It's basically the basic system is the same. your energy density in watt-hour per liter can start from around 0.2 to 2 watt-hour per liter is the range. Installation costs are also very similar. The median one is around $25 per kilowatt hours, but the range can vary depending on the location, of course. Cycle life median is around 50,000, so very large cycle life, and calendar life is 60 years. So these are the main USPs, very high life, but obviously low energy densities. Depth of discharge, if you remember from our discussions, the first time we discussed energy storage, it's the amount of energy you can extract out of the system before it has to be recovered. Okay, so the depth of discharge is around 90%. You can go up to full 100, but that is not usually done. So amount of recoverable energy is around 90%. Round trip efficiency is around 80% nowadays. Oh, so reasonably good, and this will not change between 2016 and 2030. Flywheel energy is different. So this is a nice picture of a flywheel energy system. This is your generator, this is your flywheel. This is your vacuum pump, because you want to keep this entire thing in vacuum, especially this bearing systems. So you do not have any air resistance related issues, and you are using this generator to generate the electricity and extract electricity from the external grid. Okay, this is the entire thing is on a vacuum chamber, and these bearings are specialized to reduce friction, as we have discussed before. The energy densities for a flywheel can range from 20 watt-hour per liter to 200 watt-hour per liter. So very large variation, and this is going to remain depending on the design criteria. Installation costs are expected to decrease. So 2016, the median installation cost is around $3,000 per kilowatt hour. By 2030, it will going down to a third. And so it will become $2,000 per kilowatt hour, and the range is also going to go down. Cycle life currently is quite low, around 400 cycles. It is going to increase to around 450 cycles. Calendar life is around 20 years, and it can go up to 30 years. Okay. So there is a divergence between cycle life and calendar life because there are problems with bearing wear. So if you replace the bearings, it can run again. So so the calendar life of the flywheel itself is long, but the bearings may have to be replaced from time to time. Depth of discharge 85% good. Round trip efficiency is 85%. It should go to 90% through R&D efforts in the future. So those are the kind of expectations here. Now we look at the lithium-ion battery technology. And here we are looking at multiple designs of lithium-ion battery. You can have, and these are all dependent on what is the cathode or the lithium containing electrode, because cathode and anode, the definition changes with whether its battery is charging or discharging, as we discussed. It's a lithium containing electrode. That electrode, what is it made of? Okay, lithium is there, but with lithium, what other materials are present? So if it is lithium, nickel, manganese, cobalt oxide, then it's called NMC, nickel, manganese, cobalt. So lithium, nickel, manganese, cobalt oxide, that's your cathode. Anode is again graphite. So again the other electrode for most of these cases is graphite. Okay. So this has good property combinations. So let's look at the advantages in a little bit here. Can be tailored for high power or high energy delivery. So depending on the applications, you can tailor this. It has a stable thermal profile and can operate at high voltages. This disadvantage is not really a disadvantage. There are patent issues in some countries of using it. Another very common type is lithium manganese oxide, LMO. So LiMn2O4. That's the electrode material here. The cost is significantly lower. So because manganese is abundant, okay, cobalt here increases the cost. Cobalt and nickel here. Good thermal stability, good power capability. Disadvantages: moderate cycle life, insufficient for some applications. So cycle life is lower than other types of lithium-ion batteries, and the energy performance, round trip efficiencies are usually low. Okay. lithium, nickel, cobalt, aluminum. Again, you have nickel, cobalt, but instead of manganese, you are using aluminum oxide here. Okay. So this is called NCA, nickel, cobalt, aluminum. It has also very good energy and good power capability, good cycle life in newer systems. So newer systems have a good cycle life, long storage calendar life. So those are the advantages. There are certain problems with thermal stability, and so at high temperatures its capacity can degrade significantly. So it has to be at lower temperatures, room temperature or lower, for it to perform well. So that's one of the disadvantages. Then another option you can go for lithium is lithium iron phosphate. So here it's lithium iron phosphorus oxygen. Okay, lithium iron phosphate. It has good thermal stability, so it can go to high temperatures, good cycle life, good power capability, and the costs are low because iron and phosphorus are again very low cost. But disadvantage is energy density is low because the cell voltage is low. So that's one of the disadvantages. Another type is lithium titanate. So it's lithium titanium oxygen. Very good thermal stability, so temperature does not have an impact. Very good cycle lifetime, high discharge rate capability, so it can survive much deeper depths of discharge. No solid electrolyte interface issues. So here the interesting issue here is it's the anode which is lithium titanium oxide, and the cathode can be several types. So it's a different kind of a design compared to the other 4 lithium systems. And the electrolyte is also somewhat different. The cost of titanium is high, so it's one of the chief disadvantages. It's costlier. Cell voltage is low, so you have lower energy density. Okay. So these are the various lithium battery technologies. So here it's your basic system. You have the positive electrode, the negative electrode, which is your graphite, most cases. This is your electrolyte system. Positive electrode is the metal, oxygen, lithium ion. The metal is nickel, cobalt, iron, titanium, all of those things. These are the lithium ions in between, the gray ones, and the lithium ion is moving to and fro between to create lithium carbides in the negative electrode and moving back here. So that's the kind of the idea. We discussed this before. This is the comparison between all of these. So this is NCA, lithium, nickel, cobalt, LMO, NMC and LMO. So NMC is this one and LMO is this one, lithium, nickel, manganese, cobalt oxide and lithium manganese oxide. These two have very similar properties, so they are clubbed together. NCA is somewhat different, LFP is different, LTO is different. So these are given separate charts. And this kind of compares the various types of lithium battery systems. So this is the energy density in watt hours per liter. So again, NMC LMO has the highest higher energy density values. You can get up to above 600 watt hours also, so, but there is a range from 200 to 600 for most cases. When it comes to installation costs, NC is the cheapest and the LTO is the costliest because titanium is there, followed by LFP and then these values. Okay. So NMC LMO, the manganese oxide or manganese cobalt nickel oxide, has good energy densities and reasonably good installation cost, which makes it quite good. But if you are looking for cycle life, then LTO has the highest cycle life of 10,000 cycles. The other ones have somewhat lower cycle life, though lithium iron phosphate, the newer variations, have good cycle lives as well. But the early ones, NC and NMC LMO, has lower cycle lives. Calendar life for all is the same except lithium titanium oxide case, which has higher calendar life, again because you are using titanium. So lithium titanium oxide has very good properties, but it comes at costs. Depth of discharge again higher. For batteries above 90% doesn't work. For LTO it works up to 98%. And round trip efficiency again reasonably same, but LTO has the highest, but everything is around 98, 99%. So that kind of gives you an idea of the various lithium technologies. And here you look at the research and development that has happened over like 10 years earlier that has caused this sudden growth in lithium ion technology. Okay, this is from 1991 to 2005, and you can see how rapidly R&D had decreased the cost, decreased the costs from in terms of US dollars per watt hour. Watt hour is again a unit of energy, from $3 per watt hour to around $0.2 per watt hour by the time you have reached 2001, making it commercially viable. Okay, and energy densities have increased from 2000 watt hours, 200 watt hours per liter to 500, 550 watt hours per liter. These values here, okay, the high energy density values. The specific energy in watt hour per kg has also increased to around 200 watt hour per kg. So you can see the improvement in R&D in the last decade of the first decade of the 2000 has caused the successful commercialization of lithium-ion batteries today. Now we are looking at various battery types. So let's compare all the batteries together. Okay, not just the lithium-ion batteries, and what are their individual advantages and disadvantages. So if you look at energy densities, the lithium ion class has the highest energy densities and the flow batteries have the lowest, okay, followed by lead acid batteries. Then you have the sodium sulfur batteries, etc., and then your lithium ion batteries. Okay. When you look at power densities as well, lithium ion batteries can deliver the highest power densities, and flow batteries very low power densities. The high temperature battery is somewhat higher, lead acid battery is somewhat higher. Okay, so in terms of energy density and power density, lithium ion batteries are outperforming everything else. Now when you look at cycle life, the flow batteries have the highest cycle life. So that is the advantage of flow batteries. The number of cycles till the battery can work is significantly higher. This is vanadium redox flow batteries, this is ZV flow batteries. Then in terms of cycle life, lithium titanium oxide has very good cycle life, the others not so much. Okay, but lithium ion, there are variants which are good cycle life, though they are expensive. So if you want to go for high cycle life, then that is an advantage you can get from certain types of lithium ion batteries as well. High temperature batteries have good cycle life as well, not as good as the flow batteries, but still good. Lead acid batteries have some of the lower cycle lives and comparable to lithium ion batteries in some cases. The energy installation cost, lead acid is of course some of the lowest, but the vanadium redox flow battery also has one of the lowest energy installation cost, US dollars per kilowatt, making it attractive in certain applications. Lithium ion battery is in the high end, especially lithium titanium oxide is the costliest battery so far, though it is much better quality is coming also. Okay, and if you looking at the better NMC and NMO, it has also reasonably high installation cost comparable to the high temperature batteries. So we will stop here. We have discussed energy storage technologies together, and we have ended with a comparison of the battery technologies which are emerging markets. Lot of batteries are in play. Lithium ion is the majority, but not necessarily so. There are flow batteries, there are high temperature molten metal batteries which are also competing in some applications, and there are a large ecosystem of energy storage technologies that are being developed for various applications. In the next class, we will look into hydrogen and fuel cells, which, as we have seen, has very attractive features, even though there are some features which are still require a lot of improvement and require R&D. So we will concentrate on the next class on what a hydrogen-based energy storage system will look like, and many people are talking about the idea of a hydrogen economy, where hydrogen can become the kind of a very common intermediate energy carrier that can deliver electricity and heat where it is needed without emitting carbon. So we will discuss the prospects of all of these aspects and also look at the technological process here. Okay, so that will be in the next class. So thank you for listening, and we will come back in the next class again. So thank you.